Okay, I'm going to go through an example now of this general theorem we have. The general theorem, again, is that we have a number of rotations and translations all mixed up together. And if you take a product of those, then it's equivalent to a rotation about the sum of the angles in the rotations that are given. You're about some point here. And that happens provided that the sum of the angles is not an integer multiple of 2 pi. And in the case that the sum of the angles of the rotations is an integer multiple of 2 pi, the product of those rotations and translations will be a translation. So this is the example we're going to do, and we have n being an odd positive integer, and we're giving n midpoints of the sides of an n-gon, and we want to show how you can construct the n-gon. Now it says "and" here because there actually is more than one answer, but we're going to find that an n-gon that has these endpoints as midpoints. So I'm going to go ahead and give the argument when n equals 5, so you can see what's involved with it, and more by way of an example. So I'm starting out with the n-gon, which of course we don't have at the beginning, but let's just suppose we have an n-gon, and this problem is about the midpoints of the edges of this n-gon. So let me give those names. I'll call that m1, and then m2, and so on. So m3, m4, and m5. So those are the midpoints of the sides of the n-gon, of the 5-gon, the pentagon. And I have to erase everything on the screen here except for those green dots, and then I have to recover somehow the red dots. Now this is a construction problem. It does mean by straight edge and compass, but don't worry, that'll be fairly easy to explain. We want to somehow describe how you would get back the pentagon. Now part of the reasons there's more than one answer is because I've ordered these in a certain order, and if you ordered them in a different order, so if I take m1 here, m2, then maybe m4, m5, and m3, sometimes that will change the answer depending on what we're after here. But this will give us an answer the way I've ordered them. While I still have everything on the screen, I do want to, again, fade out at least the information we don't have. But while I have everything there, let me tell you the function we're going to look at. We're going to look at this product of 5 rotations. We're going to rotate around m1 by pi, and then m2 by pi, m3 by pi, m4 by pi, and then m5 by pi. Now, there's a point here where this gets mapped to itself. How do we see that? There's in fact one point like that is we add the angles up here. We have 5 pi for the sum of the angles. 5 pi is not an integer multiple of 2 pi. It's not 2 pi times an integer. So 5 pi is what we have for the total of the angle, and we're going to have a rotation then about some point by 5 pi. So that means we have some point somewhere, and we're rotating everything around it 5 by 5 pi. So notice that means you're rotating 2 pi, another 2 pi, so you've done nothing at that point, and then you're rotating another pi. So really we're just rotating by pi around a point, because if you do 5 pi again, the first 2 pi don't do anything, the next 2 pi don't do anything, and it's only the last pi that counts. So we're rotating around some point by pi. So this f then we can rewrite as a rotation about some point p by pi. And one question is, where is a p? Is it over here, or is it someplace else? Is it some point in the picture? Well, p has the property that when I rotate about p by pi, it's not going to move. It's the fixed point. It's the one thing that's not going to move when I turn everything around p. Everything else is going to move around, apparently by pi, and p is going to stay fixed. So we want a point that is mapped back to itself. A point that doesn't move under all of these rotations. We can see that the point we want is this point P. Because when we rotate it around m1 counterclockwise, we're going to get to this point. And rotate around m2 counterclockwise, we get to this point. And then we'll get to this point, and then we'll get to this point, and then we'll be back at P. So we rotate around m1 by pi, m2 by pi, m3 by pi, m4 by pi, and then m5 by pi, and we're back where we started. So this f applied to this point gives you back this point. So we're back at p when we put p in here. And since these two are equivalent, that means this must be the same p. This is the point that doesn't move under this rotation about p by pi. So we know where p is now, this p, and we want to take advantage of that. But now let me go ahead and explain the real situation again. The real situation is that a lot of the material on the screen right now is not really there. I don't know where p is, and I don't know where any of the red dots are, or the sides. All I'm given are these green points, these 5 green points that are giving me the midpoints of the sides. And the problem is, how do I go ahead and construct where all these red points are? So we're going to do that as follows. We're going to start with an arbitrary point. I just put that anywhere. I just put it there. So we're going to start with an arbitrary point, and we're going to go ahead and apply f to this. So we start with a rotation around m1 by pi, then a rotation around m2 by pi, and so on. So in terms of constructing, what I'm doing is drawing a straight line through m1, and then I want to be over here someplace, and I get that by putting my compass here, my pointing end of the compass here, the center of the circle, and I draw a circle with this radius, and it'll get me over here where I want to be. So again, this point comes from taking a straight line from here through m1, and then drawing a circle centered at m1 with radius m1 to this blue point. And then that'll give me this other point. So that's all you do to construct this blue point. Now I want to continue that. This is a rotation around m1 by pi. I want to rotate around m2 by pi, and I should be over here someplace. Same idea. I draw a straight line, take my compass centered at m2, and with radius going from m2 to here, draw it, and that'll take me where I want to go. So this is where we're at after rotation around m2. Continuing, we go around m3, do the same thing. We get this point. Then we want to rotate around m4, we're here. Then we want to rotate around m5 by pi, and we're here. So we rotated around m1 by pi, by m2 by pi, m3 by pi, m4 by pi, and then m5 by pi. And that takes us through all these rotations. We went from here to here. Now we want to look at what this means. Well, f was the same thing as a rotation around p that we don't know where it's at by pi. But where would p be in this picture that we do know? And that is, we have to have the distance from p to this point being the same as distance from p to this point, because when we rotate around p, we're going from here to here. So we're going from here to here somehow with that rotation. So we're going around to get to there. So these two distances have to be the same wherever p is. And the other thing we know is that the angle from here to here, so the angle this point to this point to this point is 180 degrees. It's pi, because we rotated by pi. We rotate by pi from here to get here. And that's going to put p right in the middle then, because this distance has to be the same as this distance, and these will all be on the straight line. So we go ahead and draw the line between these 2 points. So again, we've constructed all of this, and we're going to draw the line we got all this constructed, and now we're going to draw the line between these two. And of course, now we need the p is just going to be the midpoint, because the distance from p to each of these was the same. So we just take the midpoint. There are different ways to do that. You might remember the first lecture I gave, we did a perpendicular bisector. So you can draw a perpendicular bisector to this line segment, and it'll go through the middle here. So we can get p just by taking the perpendicular bisector of this line segment, and that'll give us p. So now we know one of the points. We have p, and we have that point. Now the easiest thing to do to get the rest of them is to go through this construction we did earlier. You go ahead and draw a line through p and m1, and then you take your compass centered at m1 and draw a circle of radius m1p, and that will give us this part. We'll get then this. I drew a line through this, and then I did the circle radius m1p centered at m1, and that gave me this point. And then continue the process. Draw a line through here in m2, draw a circle of radius m2 from here, m2 to here, and draw that circle, and that'll give me this point. And continue. And then we get every single point then in our pentagon. So we've constructed our pentagon just knowing where the midpoints of the sides were. So given the midpoints of the sides, we're able to construct a pentagon like we wanted. So that shows us what we need to do in that problem. Again, I'm not going to do it for general n. You do have notes to look at for this if you want, but this is basically what the construction is then for showing how to get the actual pentagon once you know the midpoints of the sides. So now I'm going to go to another example of this theorem. I won't repeat this theorem over and over again this lecture, but we have this theorem and we want to go ahead and do another example. This one's a little bit more complicated. This comes from a list of examples I have online, and this is the ninth example. And rather than read all of this, let me go ahead and show you in a picture what this is saying. We're starting with an arbitrary quadrilateral, A, B, C, D. And I want to draw squares off the sides, like this. So I have a square off of each of the sides of the quadrilateral. And again, this quadrilateral can be anywhere. And I want to look at the centers of these squares. So I just drew in the diagonals here so you can see that these are the centers of the squares, M1, M2, M3, and M4. So then what I want to do is just to line up M1, M3, and M2 and M4. And what we're trying to prove is that the distance from M2 to M4 and M1 to M3 are the same, and that these two line segments intersect at a right angle. This is pi halves. Okay. Again, starting with any quadrilateral, drawing these squares, looking at the centers of those squares. When I connect these two midpoints from opposite sides of the quadrilateral and these two midpoints from the opposite sides, they're going to be the same length and they're going to meet at right angle. Okay, so again, this is what we're trying to show. M1, M3 is equal to M2, M4. And I'll write lengths that way because we also have a notation for M1, M3 being the product of two vectors. But I mean the length of the distance from M1 to M3, the length of the segment M1, M3, is equal to the length of the segment from M2, M4. And the other thing we want to show is that the angle M1, Q1, M2 is pi halves. Of course, that'll make all of these pi halves. This will be pi halves, this will be pi halves, and this will be pi halves. I went in and called this point Q1. So that's giving us what we want, the other thing we want to show. So both of those are to be shown. We don't know them at this point. We're trying to show that. So let me define a function g. So it's going to be a rotation around m2 by pi halves, followed by a rotation around m1 by pi halves. And then I'm going to have another function I'm going to call h, which is a rotation around pi 4 by pi halves, followed by a rotation around m3 by pi halves. Now remember, rotating counterclockwise, so I'm going in this direction, but just pi halves in each of these. And we can see what happens when I take C here and I rotate around M2 by pi halves, so I'm applying G to this here. It's going to go to B. And then when I go to M1 and apply M1 to that, it's going to go to A. So G takes C to A. So G will take C to A. On the other hand, H starts a rotation around M4 by pi halves. So if I do A, I'm going to go to D. Then I rotate around M3 by pi halves, D will go to C. So H will take A to C. So G takes C to A, and H takes A to C. So I'm going to combine those and call F equal to GH here. So F is equal to GH. So F is going to take A to itself because we're doing H first and then G. H takes A to C, and G takes C to A. So F is going to take A to itself. I mean, we move this down here. I claim then that F is the identity translation. Why is that? Well, it's a combination of 4 rotations. It's the rotations given by H followed by the rotations given by G, and those angles add up to 2 pi. Pi halves plus pi halves is pi, of course, and then we have that twice, so we have 2 pi. 2 pi is an integer multiple of 2 pi, so that means that F has to be a translation. That means you're moving all the points in the same direction, the same amount. So if A is being mapped to A, then F has to be, the identity translation means it's moving everything nowhere. Because you're moving all the points the same direction, the same amount, and if F of A is A, that means you're not going anywhere. So F is going to take every point to itself. What are G and H doing? Well, we already said that G took C to A, and H took A to C. What are they? Well, pi halves plus pi halves is pi. That's not an integer multiple of 2 pi. So this is adding up to pi as well. So they're both rotations around some point by pi. Now you can see what the point is. In fact, G is taking C to A again. So if you want a rotation about some point by pi to go from here to here, then it's going to be the midpoint of AC. So you want to take the midpoint of AC, and that's going to take then a rotation around that midpoint will take C to A. So the P for G is just the midpoint. Well, part of the point for saying that F of A is A, F is the identity, is that H is going to do the exact opposite. It's taking, going from here to here, it's taking A to C, going counterclockwise. So it's taking A to C, and you're going around a point to do that, and that point's got to be the exact same thing. It's got to be the midpoint, because you're rotating around the midpoint in order to get from A to C if you're rotating by an angle of pi. So both of these, H and G, have the same center of rotation. It's going to be at the midpoint of AC. So you rotate, that way you rotate around P from C to go to A, and then from A you'll go to C. So both of these are then again rotations about some point by pi. And these P1s and P2s are actually equal. And again, they're really just the midpoint of the line segment going from A to C, so right there. So what I'm going to do is to go ahead and look at what happens with P1. Both of these are the same, so I'll just call this P1 in the middle here. And I'm going to go ahead and illustrate what's happening with P1 here first. This rotation of G, we're going around M2 by pi halves to some point, and then we're going around M1 by pi halves. We have to come back to where we were. Because again, as we noted down here, G of P1 equals P1. P1 is the center of the rotation the rotation is around P1, so it's the center of rotation by pi, and we're going to end up back at P1 if we do that. So since G was equal to a rotation around P1 by pi, the sum of the two angles, we're going to be back here when we apply P1 to G. So first we go around M2 by pi halves, and then M1 by pi halves. Now this picture, this looks like a square, but there's a little bit to justify there. These two lengths are the same because we rotated by pi halves around M2 to get here, and then we rotated around M1 by pi halves to get back to P1. So these two lengths are the same. So we have these two lengths from M1 are the same, and these two lengths from M2 are the same. But why are these the same as each other? So why are all four of them the same? And that, of course, has something to do with the fact that we have right angles here. And we can see that by just drawing in this line here. If you draw in this line, you have a right triangle here, because this is a right angle. And this is equal to this. So this will be an isosceles right triangle, which means that these two angles down here at the bottom will be 45 degrees. And the same thing down here. We'll have these two sides being the same, if I draw in that side here, these two will have to be equal because it's an isosceles triangle, and this is a right triangle, so they'll both be 45 degrees. So that's going to make this 90 degrees and this 90 degrees. And so all of these will be 90 degrees, and you'll end up with a square. The same thing happens over here. I went ahead and looked at what happened to P1 after I rotated around M4. It's going to go over here. So these lengths are the same. I rotate around M3. It's going to have to come back to P1 because h of P1 was also equal to P1, as we have down here. So these lengths are the same, these lengths are the same, and they're all going to be the same again because you can argue that these are right angles, all of these are right angles. So it's going to be a square in part because if I draw on this diagonal, you can see that this triangle up here is congruent to this triangle down here. They have an hypotenuse in common, and they have the same angles. They're both 45, 45, 90. So the angles are going to, and the hypotenuse are going to give you that, being the same, are going to give you that these sides are also the same. So we have two squares here. And this is already kind of interesting in itself. These two squares we've drawn here happen to go through the midpoint of AC. So again, the segment AC, P1 is the midpoint of that. So we have that information. Now I'm going to use what we have here, and notice that if I take the triangle P1, M1, M3, so we're going from P1 to M1 to M3. That's this one, M1 is here, M3 is down here. So this skinny triangle here. And I want to rotate it around P1 by pi halves. So I'm going to turn it in this direction, pi halves. The whole triangle. Well, just look at what happens to this side. If I rotate it by pi halves, this is going to come over here because this was part of that square we just had. So this side is equal to this side, and this is pi halves. Okay. So if I rotate around P1 by pi halves, M3 is going to go to M4. And notice if I take P1 rotate M1 about P1 by pi halves, it's going to go to M2 for the same reason. Again, this was part of a square we had, so these sides are the same, P1 to M1 and P1 to M2. And if this angle is pi halves here, so M1 is just going to go to M2. So if you imagine taking this whole triangle and rotating around P1, well, this side goes to here, this side goes to here, and that's going to force this triangle to fall right on top of this one. Okay, the third side's going to have to also. Or put it another way, this side is equal to this side is equal to this side. So these two triangles, this one here and this one here, are going to have to be congruent because when I rotate by pi halves, I'm taking this angle and putting this one up there. This one's coming over here, and so these two angles are going to be the same as well, these center angles. So we're going to have by angle side that both of these two triangles are congruent. In any case, you get this triangle by rotating this triangle around P1 by pi halves, and so these two sides, M1, M3, and M2, M4, are going to have the same length, which was one of the things we wanted to show. So that's all I was saying down here, is that the rotation around P1 by pi halves of this whole triangle is going to this other triangle that we were just describing. So we get M1, M3 is equal to M2, M4. Now I've added a couple points in here, Q1 here and Q2 here. And what we want to argue is that we're still trying to show that this angle is a 90-degree angle here. So we need to justify this as 90 degrees. So what I'm going to do for that is I'm going to look at the triangle M1, Q2, Q1, and I claim it's similar to triangle M2, Q2, P1. So here are the two triangles. I have this triangle going from here to here to here, and I claim it's similar to this triangle going from M2 to, I went to Q2 to P1. So M1 to Q2 to Q1 will be this similar to M2 to Q2 to P1. Okay? So why is that? Well, you can see because of these lines crossing here that these two angles are the same measurement. And these two triangles, again, we have that were congruent, these long ones, is going to give me that this angle here is the same as this angle. So these two angles are the same, and these two angles are the same. And so the third angles have to be the same because all the angles have to add up to 180. So if two of them are the same, the third one has to be the same. So, but in particular, this was a right angle because this was part of that square we had earlier. And so this angle has to be a right angle as well. And that's what we're trying to show, that these were right angles, that this was a right angle right here. And that's where that comes from, again, because these angles are the same, these angles are the same, and so these two angles have to be the same. Since this is 90 degrees, this has to be 90 degrees. So that shows the second thing we wanted to show, that angle M1, Q1, M2 in this picture is a 90-degree angle. So that shows us everything we wanted. We get that the two lengths, this length here and this length here, are both the same, as well as having a 90-degree angle where they intersect. So that finishes this problem and this lecture.